There we go. Okay, welcome everyone to what I think I've counted as our 68th Reading Online Sport Economics Seminar. This is our second in the autumn of 2021, a good 19-20 months after the pandemic began, but we're meeting online and hearing some of the best sport economics research that there is out there. We've been very fortunate to have many excellent talks over the last year and a half. And we continue that today with a talk by Bernd from the University of Paderborn on the impact of team size on performance in the absence of shirking clean evidence from elite rowing contests. So in many firsts during the pandemic, this is the first talk, I believe, on rowing. So I'm looking forward to your presentation, Bernd. If folk can keep their microphones on mute, that will be really handy. I'm sure Bernd will be happy to take questions for clarification as we go through, but there's going to be plenty of time for Q&A at the end. Bernd has about an hour in which to talk, so not to take any more time from Bernd, please do take away your talk, Bernd.
Can you see my slides?
I can, yeah. Do you want to put it in full screen?
So everybody else should be able to see them too.
Yeah. I think so. Yep, perfect.
Welcome everybody to today's, I think, 68th edition of ROSES. This is joint work with Johannes Orlowski from the University of Zurich. And the title is, as James already mentioned, the impact of team size on performance in the absence of shirking, clean evidence from elite rowing contests. I will be a bit more specific what we mean by clean evidence and why we think that shirking is completely irrelevant in the context that we are looking at in a few minutes. So let's get started. It's trivial to say that larger teams are typically able to complete more tasks and are therefore more productive than smaller teams, or they may be able to complete one and the same task in less time than a smaller team. However, increasing the size of a team is not always accompanied by the expected increase in performance. Even if all individuals possess the abilities and the expertise required to complete their task, they may fail to coordinate their efforts in a productive way. This has first been documented by a French agricultural engineer named Ringelmann in a famous experiment, the results of which he published in 1913. So the question we try to answer in this paper is, what is the optimal team size? Before we get closer to our research question, let me say a few words about the Ringelmann experiment. So Ringelmann asked his students first to individually pull a rope and to move some weight. And then he increased the size of the team. Initially one person, he added a second person, he added a third person, etc. And after having measured each individual's performance, he developed that expected performance line and compared it to the actual performance he measured. And what he found is the difference between expected and actual performance increases with team size. And his argument as an engineer was, it's apparently difficult to coordinate larger teams. So he did not pay any attention to what economists typically refer to when they talk about shirking. For Ringelmann, it was simply a matter of size of a particular team. From an economic point of view, well, we are all familiar with the classic Elkin and Demsetz argument, stating that when a team performs, it's extremely difficult to measure an individual's contribution to the team's performance. And the more difficult it is, the more pronounced the incentives are for each individual to hold back his or her effort at the expense of the other team's members. So when individuals come together in teams to perform a particular task, their performance not only depends on their individual resources like talent, skills, and effort, but also on the interaction within the team. Again, going back to the standard economics approach, a loss of motivation occurs when rational utility maximizing individuals work in teams compared to when they work alone, because team members tend to rely on the effort provided by co-workers. So what this suggests is it is not yet entirely clear whether a lack of motivation or a lack of coordination deters teams from exploiting their full potential. In recent years, psychologists have started to look at this issue too, and when economists refer to this behavior as shirking, the term used by psychologists is social loafing. So these are synonyms, to make that clear from the outset. How can you reduce shirking? Well, you can first of all increase monitoring, because when team members feel their individual effort or output is identifiable and subject to evaluation, they are motivated to exert greater effort in an attempt, for example, to avoid being kicked out of the team. You can increase the individual's involvement by attaching rewards or punishment to the task contingent on the performance of the group as a whole. That means you incentivize team members to monitor each other. Third, you can increase team identification by emphasizing the importance of the individual's respective roles in the team. And fourth, you can establish clear, explicit goals to increase team members' commitment and effort exertion. We use data from elite rowing contests, and since I assume that not everybody is equally familiar with rowing competitions, I will say a few words about the institutional framework or the institutional setup. All elite rowing competitions take place on a 2,000-meter course, regardless of boat type or boat class. I will say a few words about boat types and boat classes in a minute. So all the competitions included in our data set took place on a 2,000-meter course, mostly on artificial lakes, sometimes on rivers, but typically on a lake. In each boat class or boat type, 6 boats qualify for the finals in a series of heats and semifinals. And after 500, 1,000 and 1,500 meters, split times are recorded for each contesting boat. So that means we can calculate how far is the leader ahead of the second placed boat, how far away of the third placed, or we can vice versa calculate how far behind the leader is the second placed, how far behind the second placed is the third placed boat, etc. It has been documented in the literature that the pacing strategies do not significantly vary between winners and losers. So nobody starts slowly to increase the boat speed towards the end of the race or vice versa. So pacing strategies seem to play not a particularly important role in our context. Here you see the different boat types and boat classes. So there are 8 different boats. And what is first of all important to distinguish is between scull boats and sweep boats. And you can see what the difference is. In scull boats, each rower is equipped with 2 oars. So he has an oar to the left and to the right-hand side of the boat. And in sweep boats, each rower is equipped with one oar only. And that makes sweep boats more difficult to coordinate than scull boats. It's more difficult to stay in the lane, in the middle of the lane, if each rower has one oar only. And some of the sweep boats do not only have rowers on board, but also a coxswain, a person whose task it is to coordinate the activities of the rowers in the boat. And this white dot represents the coxswain. So the coxswain only brings weight to the boat and may therefore slow the boat down. If you compare, for example, the pair with the coxed pair, the question is the coxswain's additional weight that he brings to the boat, does this negatively affect the performance of the boat, or do the coordination activities that he performs or she performs outweigh the negative effect of additional weight? And as you can see, there is, for obvious reasons, no sweep boat with a single rower. He would row in circles instead of moving ahead. And since there is no equivalent to the sweep 8 among the scull boats, what we look at is only 6 boat types and classes. So we compare the double scull with the double pair and the double coxed pair, and we compare the quadruple scull with the 4 and the coxed 4. All these boats, or most of these boats, are also rowed by either female rowers or by lightweight rowers. You may be surprised to hear lightweight rowers, and there's a very simple explanation for that. Typically, rowers are very tall and very muscular. So the average rower is about 190 meters tall and has between 85 and 90 kilograms. And in an attempt to make rowing more popular in countries where the population is typically not that tall and not that heavy, the International Rowing Federation in the early 1970s introduced lightweight classes, and we have also included them in our data set. So we observe lightweight rowers in the quadruple scull, in the coxed 4, etc. But they compete only among lightweight rowers. They do never compete with these taller and more heavier guys. And we have under 23 and we have junior rowers. I'll come back to these results in a few minutes. So our first hypothesis is larger boats, and that sounds trivial, are faster than smaller boats. However, since the coordination costs increase with team size, an improvement in the observable performance will not be linear. Second, since boat classes differ with respect to coordination complexity, scull boats will be faster than sweep boats. Third, boats with a coxswain may be easier to coordinate than equally sized boats without a coxswain. However, the coxswain brings weight into the boat, and it is not clear whether this additional weight is offset by the coordination activities, and we expect the effect of the coxswain in a boat with 4 rowers to be different from the effect of the coxswain in a boat with 2 rowers. And finally, rowing is a physically very demanding sport, and therefore we expect female boats, lightweight boats, and junior boats to be slower. Where does the data come from? We have individual race data on 137 international top-level competitive rowing events between 1960 and 2018. The available data goes back, I think, until the 1920s, but we have excluded races before 1960. The results are more or less the same when we include older data, because we always include in our estimation year and event fixed effects. The data were collected from the official website of the Fédération Internationale des Sociétés d'Aviron, and we restrict the sample to final heats only to avoid bias occurring from strategic behavior. So if you know your rivals, you may have an incentive to rest your best rowers in an early heat. And therefore, strategic behavior cannot be ruled out early in a particular contest. And second, we restrict the sample to boat classes with 2 or 4 athletes only for the reasons I've just mentioned. There's no equivalent for an 8 among the scull boats, and there's no equivalent for the single rower in the sweep boats. And we include only complete heats, so no dead races, no disqualifications, or the example, James, that you have just mentioned with the English 4. If they deterred the opponent, this race would not have been included in our dataset. So our sample includes 9,333 boats in 1,613 heats. If you divide 9,333 by 6, you end up with a figure that's different from 1,613. So what is included are heats where one boat drops out of the race, for example, because one rower broke his or her oar. This is still included, and this slightly reduces the number of boats crossing the finish line. But this is never at the detriment of other boats in the race. Here you can see where our data comes from. 1.21% of the observations come from Olympic qualification races, 505 from Olympic races, European Championships, World Rowing Junior Championships, Under 23 Rowing Championships, World Rowing Championships, and World Rowing Cup. So these World Rowing Cups are held every single year, and therefore the number of observations is, and there are more World Cup races in a particular year. So it's 5 to 6 events per year, and therefore the number of observations is particularly high here. Nearly half of our observations come from World Rowing Cups. The Olympic Games figure is not that large not as large as you might expect, and the reason is not all these boat types and boat classes that I've outlined a few minutes ago are on the Olympic program. So in our estimations, we progress in 2 steps. Step number 1, we regress individual boat types on finish time to assess the relative importance of team size, task complexity, scull versus sweep boat, and additional monitoring or coordination, coxswain present or absent, on the performance. That means the finish time. And in a second step, we try to analyze the effect of relative prior performance on the future absolute performance. So how do teams who are ahead or behind perform from one split to the next, taking into account differences in team size, differences in task complexity, and differences in monitoring or coordination activities. As I've already mentioned, we include event year dummies in the estimations for a very simple reason. This allows us to assume that weather conditions are identical for all the boats involved in a particular race. And this takes into account technical progress. The boats that were used in the 60s and 70s looked completely different from the boats that are used today, and we control for these advances in technology by including event and year dummies. And we also control for gender, age class, and weight class of the rowers involved.
Bernd,
and in
Bob's
our
got
second
a question for you.
Yeah.
Bob's got a question for you.
Yeah, I just wanted to step in here because you were talking about technical progress on the boats, which I guess is to do with materials and boat design. So you've got year dummies, that's great, but are there any kind of threshold effects when there's a particular innovation, a particular design change in a particular year that you can look at?
To be honest, we haven't done that, but my answer to this question would be, since we have elite rowers only, they are likely to benefit from steep jumps in technology to the same extent. You can now argue, well, some teams might better be able to cope with these changes than others. Well, those who are not able to cope with these rapid changes will not qualify for the final heat of a world championship or an Olympic event. However, what we can try to do is check for particular important changes in technology. So far, we haven't done that.
Thanks.
Okay, so and in the second model, we include interaction terms for time differences between the contestants with respect to team size, task complexity, and monitoring. So how do we calculate this? As you can see here, how far behind is the third placed boat behind the second placed? How far behind the first placed is the second placed boat? We do not have that information for all these 9,333 boats. These split times are available only since, I think, late 1970s. But when we estimate our first model with the restricted data set, only including races from the late 70s to 2018, the results are completely unaffected. So here are the descriptive statistics. Average finish time is 402 seconds. Recall, this is a 2-kilometer race, and you see the minimum is 332 and the maximum is nearly 560. So there's a lot of variation. And the same accounts for the split times. What you see is the split times are pretty much the same. So that means the boats are all at about the same pace. And that refers to my argument that pacing strategies of leaders and followers are virtually identical. How far behind the next rival are you at 500 meters? So it's 0.7 seconds, and that increases towards the end of the race, not surprisingly. However, there are also very close races in our data set where the next rival is 0 seconds ahead, where you are at par with the next rival. And you see here the distribution in our data set. 22% are pairs, 30% are double sculls. Coxed fours are not on the Olympic program and therefore are rather rare in our data set. The fours, 90%, and the quadruple sculls, 22%. Nearly half of the boats are sweep boats. The other ones are scull boats. 20% of the boats are coxed. team size 4, 45%, and that means team size 2 is 54%. Female, 38%. Our data set starts in 1960. World Championships for women have first been held in 1974, and therefore the number of observations is smaller than the number of observations among men. Juniors, about 10% of the observations, lightweight rowers 33%, and under 23, 15.5. Descriptive box plots of finishing times. You see there are outliers in each boat class, but what is apparent is that the speed of the boats differs significantly, not only with respect to size, but also to task complexity and monitoring. And this will become more clear when we look at the first regression results. Remember, the overall finish time is the dependent variable, and the Cox pair is the reference boat. So that means the pair is, other things equal, 30 seconds faster than the Cox pair. Or to put it in other words, it may well be that the coxswain performs an important task in coordinating the activities of the rowers. However, the additional weight is detrimental to the speed of the boat. The double sculls, 2 rowers, each equipped with 2 oars, is 46 seconds faster than the coxed pair, and that means the second oar makes a boat about 16 seconds faster. The difference between 46 and 30. And that's what I argued a few minutes ago. Scull boats will be faster than sweep boats. When we look at the Cox 4, that's 54 seconds faster than the Cox pair. So that means using the same technology, 2 additional rowers make the boat 54 seconds faster than the reference boat. And when you now compare the Cox 4 with the other 2 boats with 4 rowers each, then you see that the additional weight that the coxswain brings to the boat is not completely offset, or on the opposite, a boat with 4, either equipped with 1 oar each or with 2 oars, outperforms the Cox 4. So the quadruple sculls are about 77 seconds faster than the Cox pair, but they are also 9 seconds faster than the 4, and they are 23 seconds faster than the Cox 4. So the coxswain, bringing additional weight to the boat, slows the boat down, irrespective of the coordination activities that he or she performs. And when you go to YouTube, you find dozens of videos where the important role of the coxswain is emphasized. However, what we see is that the additional weight he or she brings to the boat slows it down considerably. There is a minimum weight for coxswains. Clearly, the incentive of the rowers would be to have a very tiny person in the boat. In the men's races, the minimum weight of the coxswain is 50 kilograms, and in the women's races, it's 45 kilograms. And these persons are typically not only very light, but they are also not that tall, and they are mostly hidden in the boat. Pictures that are available on the internet clearly show how the coxswain is more or less hidden in the boat. However, what is important to emphasize, the coxswain sits in the opposite direction. The rowers have the finish line in their back, but the coxswain looks towards the finish line. That means the coxswain is always able to identify how far behind the other boats his own boat is, and therefore he may change the strategy depending on the position of the boat in a race. So the rowers see the boats who are behind them, while the coxswain sees the boats who are ahead of the boat that he's responsible for. We see that, boats with female rowers are 43 seconds slower than male boats. Junior boats are 20 seconds slower. Under 23 are 67 seconds slower. And what I find personally surprising is lightweight rowers are only 7.6 seconds slower than normal, in quotation marks, boats. And this is surprising insofar as the average weight of the rowers in a lightweight boat must not exceed 70 kilograms. Standard rowers are between 85 and 90 kilograms heavy, and that means they have far more muscle mass to move the boat. And lightweight rowers, who are on average 15 to 20 kilograms lighter than standard rowers, are only 7 to 8 seconds slower. So that means here again, additional weight plays an important role. So the relationship between team size and performance seems to differ with respect to task complexity. The marginal returns from team members seem to be larger for more complex tasks. Second, the marginal returns to a presumably less complex task, scull versus sweep, are decreasing with increasing team size. And the additional monitoring seems to be more than offset by the additional weight of the coxswain. However, the negative effect on performance appears to be weaker for larger teams. Because if you have 4 rowers who move the coxswain, this weight plays less of a role than if you have only 2 rowers responsible for the transportation of the coxswain. So when we look at the split times, NRL is next rival lead. How far are you behind the next boat in the race? And for the leading boat, that difference is clearly 0. But what you can see is the next rival is ahead by 0.9 seconds at the 500 to 1000 meter split, 0.7 seconds at the 1000 to 1500 split, and slightly less in the end. But this difference is very, very small. What we see next is the split is nearly constant. The setback is nearly identical across the splits when we look at a team size of 4. And when we interact team size 4 with the next rival lead, the effect is very, very small, yet statistically significant. When we look at sweep boats, so sweep versus scull boats, the difference is smaller. However, when we interact that with the time of the next rival, with the difference, that is again tiny but statistically significant. Same for Coxed boats. And when we go further down, the time behind for female boats is identical across the three splits. For juniors, it's identical. Under 23, it's basically identical. And for lightweight, it's slightly increasing. So the latter finding suggests that lightweight rowers have less stamina, which is not surprising given the significantly lower body weight. So when we look at these interaction plots, you can see that team size, task complexity, and additional monitoring have different impacts on the team's performance. So the predictive margins of teams with 4 rowers, of sweep versus scull boats, and of coxed versus uncoxed boats. This suggests that the impact of team size, of coordination complexity, and of additional coordination activities varies across the different boats. So experiencing a setback, that means a poorer relative performance, does seem to negatively influence future absolute performance. When you are back early in the race, that has an impact on your further performance in that particular race. And the magnitude of this detrimental effect, however, decreases with the progression of the race. Larger teams seem to react more sensitively to setbacks. However, this effect is rather small in magnitude. Sweep boats, which are characterized by a higher task complexity, seem to react significantly stronger to setbacks than scull boats. And finally, the relationship between setbacks and performance is significantly weaker for teams with additional monitoring. That means the coxswain, and that has to do with the fact that the coxswain is able to observe the boats that are ahead of his own boat, while the rowers themselves see the boats that are behind them in a particular race. Conclusion: in the absence of shirking, team size, task complexity, and monitoring are related to team performance. Let me emphasize again, since we include in our data set, in our econometric analysis, only finals of important races, we conjecture that shirking should be completely absent. Everybody who is in an Olympic final wants to perform as good as he or she can, and therefore shirking is highly unlikely. Relative prior team performance negatively relates or affects future team performance, and there's and the nonlinear relationship between team size and performance seems to be a motivational problem rather than a coordination issue. Well, there might be different incentives for the rowers to perform adequately, so we may add either dummies to control for the importance of the contest, a dummy for Olympic Games, a dummy for World Championships, or estimate the models separately for these different events. We have not yet done this. That's all we have, until now, I'm looking forward to your questions and comments, but before I hand over, let me thank you for your attention and your patience. Thanks a lot.
Thank you very much, Bernd. Very interesting talk indeed. And as I said, the first talk on the Roses series on rowing. Any questions and comments? None so far. I'm afraid I've not got a stock question ready to ask you, Bernd, unless I'm missing any hands being raised on my computer.
Does that mean the talk was completely boring, or was I able to make everything clear? I don't know.
I would say it was certainly very interesting. I posted in the chat the video of the British rowers almost colliding with Italians. It was, so you can have a look at that.
Yeah, definitely.
Questions and comments.
Well, let me ask a question. Do you all find our argument convincing that shirking can be completely ruled out in this context?
Because you exclude heats. These are only finals of events that matter. It's not a hill that I've ever wanted to really die on, is the shirking versus no shirking issue, but it's hard to imagine you would shirk in a final of a major event.
See, the rowers have to be synchronized perfectly. And if one is a tenth of a second too late to put the oar into the water, this will ruin the entire boat's performance. So shirking is immediately observable, even to an ignorant like me, who's not that all familiar with the sport. And I have never seen an Olympic race or a World Cup race with a poorly synchronized team.
I might have a question. Can you listen?
Yeah, sure. Please go ahead.
Okay, thank you very much, Bernd, for the interesting topic. I could only join it a little bit late, so I might have lost some. But my question is more general. In some cases, we try to make use of data on sports and then to come up with a broader implication. In that case, I suppose in teamwork and the effectiveness of this synchronizing might be resembled by how well do teams cooperate in firms. So do you plan to expand the implications of this, or to what extent do you believe we can jump from a context of sports into a more general management context there?
I think there are certainly contexts where the results are easier to transfer than by looking at rowing. Because if all what we observe is a matter of coordination, that implies that each individual's contribution to the team's performance can easily be measured. And that makes rowing teams rather unique, right? When you think about football or basketball as other team sports, and I consider rowing as a team sport, the individual's contribution is much more difficult to measure in the examples I've just provided. And therefore, distinguishing between coordination problems and motivation problems is far more difficult in basketball and in football. In rowing, it's simply a matter of coordination. So whenever it is easy to measure an individual's contribution to the team's performance, then you can argue when the team does not exploit its full potential, then it must be due to coordination costs. The pity is we do not observe a boat with 8 rowers who are each equipped with 2 oars. That would further open up opportunities to exploit the relative importance of team size on performance. So since the 8 is only observed with a coxswain and 1 oar per rower only, there's no comparison boat. And therefore, that certainly limits the generalizability of our results to a second extent.
Thanks, Pedro. Thanks, Bernd. Hannah has a question.
So with regards to the lightweight rowers, do you look at their heights to look at cooperation? So coming from the point of view as a rower, lightweight rowers who are taller are less likely to so-called cooperate because they're more fatigued if they're taller because they've used unhealthy methods to cut weight. So do you look at height differences in terms, particularly with lightweight rowers, in cooperations, and if they're out of time because they're distracted based on weigh-ins, if you know what I'm...
Yeah, there is, yeah, I know what you mean. So the pictures I have seen from victory ceremonies, for example, seem to suggest that the winning boats have rowers of more or less equal size. So there's not much of a difference in the height of the lightweight rowers. But what is an issue in lightweight rowing is that, similar to weightlifting, for example, some rowers use strange medication to reduce their weight. But we don't have systematic evidence on that. And the positive doping tests that we do observe in rowing, interestingly enough, mainly come from lightweight rowers. So there is something going on, but unfortunately we cannot control for that in our estimations.
Okay, thank you.
Thanks, Hannah. Thanks, Bernd. Alex has put in the chat, how much can resources and or funding explain time differences in rowing, and are there ways to control for that?
Well, that's certainly a problem. There are, let's say, traditional rowing countries, and that suggests that some countries spend more money on their rowing teams than others. And perhaps surprisingly, it's not only the UK and the US and Australia and New Zealand, but it's also a couple of rather poor southeastern European countries who are very successful in rowing. So it's not the, let's say, GDP per capita that can explain success in rowing. It's something more like path dependence. Previous success contributes to increased funding and therefore leads to future success. But we have not in detail looked at that issue, to be honest.
Okay, thanks, Alex. Hannah, you're on mute.
Just with rowing, have you looked at corruption in terms of people keeping in time? So let's say the corruption scandals when people stress with athletes and bullying.
We have not yet considered this issue at all, no. Do you have
So there's a lot of data.
anecdotal evidence?
There's a lot of data from New Zealand, actually. I think it was the London Olympics. So the two, I forget their name, they're short. So there was evidence when one of the fours went out of time and they blamed the shorter rowers. There was a lot of evidence coming out on bullying when that was coming out from other teams. So corruption and bullying and how that plays, and also betting within rowing. So deliberately not cooperating, because at such an elite level, it's very rare for somebody to come out of stroke. So looking at just the betting and the corruption and the bullying within rowing and high performance rowing. And there's evidence in New Zealand, I know.
Okay, is this betting data available?
There was some data available. I never looked into it in very much
Okay,
detail.
that's a great suggestion. We should look at that. Yeah.
Great, thanks, Hannah, and thanks, Alex, as well. Any more questions and comments? Okay then. Well, thank you very much, Bernd, for a very interesting talk. Thank you to all of the participants for interesting discussion as well. It was very good to have the first rowing talk of the Roses series. We don't have an event next week, September the 17th, which is just before our academic year begins in Reading. But we have a talk in 2 weeks' time by Niall Friel from University College Dublin on assessing competitive balance in the English Premier League over 40 seasons using a stochastic block model. So please do join us for that. And I do wish you all a good weekend. Thank you very much for your attendance.
Thank you very much. This paper might make its way on your desks as a referee or a reviewer in the not too distant future. Okay, have a great weekend. Thanks a lot.